Now I can start. So, can we start? Yeah. My topic for today is the first part of overcurrent protection. Molecular MSA, maximal Strauss aizsardzība. Protection of maximum current. Most popular, most used kind of protection. Protection operates if current. Protection operates when current is bigger than, ko nozīmē nostrāde, trip current. Nostrāde, trip. So it's setting if current is above an operation or trip threshold. Sounds very easy. The source, the switch, your current from current transformers, your device operating disconnection signal. Easy? It sounds easy. It's not so easy when you look deeper. Now I'll try to explain. Let's say we have simple network. One line, second line, and let's say this is, for example, 10 kilovolt middle voltage network, and very simple schematics. Again, zero for customer. I'm simplifying and not showing loads along the line. I need to draw one chart. A, B, C, and D. Protection. Chart. If we have a fault, line to line or three-phase fault at a distance from the beginning. So it will be fault current what observed this transformer. Fault current as a function of distance. Three-phase two. What's the distance between these two lines? Distance between lines. What's the ratio between line to line and three-phase fault in such simple network? You should know it from transients. Square root of 3 divided by 2, or 0.866. In such radial network, at first, 0.866. Also, I can draw this blue line. What it will be? E1 max. What is this? 2 volts. Yes. If we speak on protection here at substation A, what are requirements? 2 lectures ago we spoke. Requirements. Protection should be sensitive and selective, yes? Sensitive. Should operate on any internal fault. marking with the red dot. It's a minimum internal current. Internal for protection A. So your protection should operate safely on this current. Agree? That's me. Here is the gap for my protection operation current. Yeah? It should not operate, should not trip falsely on load, and should operate safely on minimal internal. Yes? So I need to take some safety margin, maybe 10%, and draw, do I have some? Here is Mostrad A, or trip current for protection A. Agree? Am I correct? Hello, oh sorry, Akshihita. Hello. So, wait 1 second. Hello. I need to repeat. I have this simple network, and these are fault current as a function of distance, three-phase and line-to-line fault. I assume this is isolated neutral. And here I took gap 10%, like this, from minimal internal fault current to get this nice orange line. I hope you can see it's orange. This orange line is a first approach for the trip current of this protection A. Yeah. What can we tell? What should we say about my design? Where is the real operation area or zone for my protection A? Where it ends? Here it ends. Is it selective? If I have, okay, this is fault number 1, fault number 2. It's an external fault. External. Where the max external fault will be? I think this one. This is, I need, okay, I will draw it in yellow. I hope it will be visible. This is E, max external. In Latvian, it's maximala area strāva. So it's maximum external current for my protection. Here. What can we say about selectivity? What was the sound for selectivity? Should not operate in case of maximum external current. Yes? Do you understand where am I? Here is my trip current, and here is my external current. In reality, protected area extends up to end of next of adjacent line. Is it okay? Will this project pass? What's your opinion? it okay? When I have operation area extended up to end of next line, is it selective? No. This will not go. With such design, I will get what I will get. I will get direction to the door. My next position will be shallow operator. And if you will try to do something, you also have a good chance to be a shallow operator. Okay, what should I do? I can try to make my protection selective, yes? To ensure that it's selective, I should choose plus 10% and draw this line. This will be version with 1.1 E max external. Is it okay? What is effective protected area? Only this part. This area will remain unprotected. What will happen? I will be advertised to shallow operator. Do you see problem? I see. Where the problem is? I need to fulfill two criteria. Selectivity and sensitivity. But I have only one coordinate here. Trip current. I cannot sit with one S on two chairs. I cannot fulfill two criteria with only one parameter. I need second one. I need second coordinate. So this idea is simple adjusting. Trip current will not work. Where to run, what to do. (1964). This is old overcurrent relay. It has winding, core, nice, where am I? Up here. And I said here of nice silver. The contacts were made of silver. It's plate against them. This is overcurrent relay. It just sends signal current is above. I will add second element. Here is element number 2. Time delay. It has a clock, pair of contacts which are closing when time elapsed. It's an end. This turn, nice coil. If you apply voltage to coil, clockwork starts and relay counts 2.5 seconds and then sends a signal forward. Very simple time delay function. Wait for 2.5 seconds and then send a signal. And what if input signal disappears within until output signal is sent? What happens? You see, it's returned to its previous condition. Input binary signal should present all 2.5 seconds, all delay time. If it disappears or it's cleared before output signal sent, delay function returns to its original, to its zero state. Yeah? Now, how it will work? So, this is useless. We will have schematics. Overcurrent, overcurrent, overcurrent. A phase, B, C. Time delay, disconnection signals. Delayed operation. If any of current is above what? Above orange line, delay starts, waits designated time, and then sends signal to disconnect. Easy. Sounds easy. This is here. More orange line. This orange line is here. For my protection B, I can, if I would like to have max possible sensitivity, what should I select? Equals to 1.1 E or add maximum. You understand what I'm doing? I'm selecting most sensitive version of all. Here I can do this way, but I can do it better. I will make it as sensitive as possible. 1.1 E or max. Now they are as sensitive as possible, but they will not. You will say, oh yeah, but they are not selective. To achieve selectivity, this is time. Nostrad means operation time. Time to trip. For B, it will be 1 time space. For A, it will be 2 double delay. For B, 1. And what kinds behind this? What is? I'll explain 1 second. First, let's try to understand how it will work. Let's say we have this fault number 2. Where is current of fault number 2? Here it is current of fault number 2. Yeah, here it is. What happens with current function of A? Where is the trip current? Here. Is this red dot above? Above. Will it start? It will start. What about B? Here is the current, trip current for B. Will it start? Also above. Both starts. So, both relays do click and send binary 1 to their time delay function. Both start counting. Both clocks work. What happens next? B needs to count only 1 time space. A counts 2 times space. Both. And what happens? B arrives first. Yeah? B sends disconnect signal to its circuit breaker. What circuit breaker do? Of course, what is intended. Disconnects. Network clears fault. And current disappears. Current disappears. What happens with current relays in A? No currents, no binary. 1. They return. Do I have some visible? Wait. Oh. Maybe this one. No. I'm afraid it's gone. Okay, I will return it manually. Coil, it will go. What it will go back. And what happens with time function of A? Returns no signal sent. Yeah, because it returns. They are sensitive. Yes. And are they selective? Are they? In such schematic, selectivity is achieved by time delay. They start both, but because B has a smaller time delay, it operates first and disconnects faulted line. Idea is to have time delay decreasing from the center of supply. Time delay should decrease this way, from the center of supply, to make tail protections operate first. Understood? Now, what's the spacing between? Spacing between protection, this gap, delta t, delta time, is selected first, starting from first. Current should disappear. U first start with your circuit breaker. What time is necessary for circuit breaker to interrupt an arc? For very old circuit breaker, it may be 2-3 seconds. For 16th designs, it may be half second. New circuit breakers do everything less than 200 milliseconds. Guaranteed. Second, you need to give some time for circuit breaker mechanics and some spacing for your time function error. So for average, for distribution networks, average is half second. Spacing of half second fulfills any, except extremely archaic circuit breaks. If you have modern equipment, everything fine, SF6 or better vacuum circuit breaks, or you can reduce time gaps to 300 milliseconds. Yeah, it's nice, but I need to point one problem. I think it's okay to erase this. I need to point one problem. For example, 1 segment, 2 segment, 3. Here is your end customer. And of course, everywhere customers, I'm simplifying. A, B, C, D. D will have one time space. Small. Actually, you coordinate with this breaker. So, D, one time space. What will have C? C, two time space. B, three time space. Because you need always the safety margin. And A for delta. This is operation time. Need your opinion on such schematics. Is it good? Where's the problem with these schematics? You think it's good? $500, 1,000, 1,500, 2,000 milliseconds. This is 2 seconds of delay. When the current is, fault current is maximum. When fault is at the beginning of your supply chain. When the delay is maximum. At the beginning. I don't think it's a very good idea. What to do? We can cannot cut delay time because we need to maintain selectivity. We cannot cut delay time for whole line. What can we do? Remember my yellow line. So here is D1. I can incorporate two sets of overcurrent relays. One, what can I do? This will be very, very current. And they will operate with zero delay. Instant protection. Plus another set current grade. Idea is have two sets of overcurrent function. One instant, one delayed. Instant will operate with delay 0. This one is delayed. Why I'm showing these two GT marks? Remember yellow line, selective protection. When I tried to do it selectively, I had higher current above. It's a... For this part, what's the criterion? This part is from rho at mass. For this part, this threshold criterion is a max load current. For this, max current of max external fault. This part is selective, made selective. It's current. It is not so sensitive. It protects only beginning of the line, but it's fast. This part is sensitive, but it's slow. For B, I will have instant B1. This one is near 0 operation time. B2. A1, A2. Here is schematics. At last, beginning of the line is protected instantly. I reduce here also. Here, become familiar. (1966) protective box contains 1, 2 relays for high currents, 1, 2, 3 relays for not so high currents, time delay, one special relay, and set of indication relays. 1 second. I will draw how it was in 60s. Because we deal with distribution networks, it's bit made cheaper. So we have what we have. Okay. A. What is K? Relay, A, amperes. So these are 2 overcurrent relays for phase A and C. This box intended for network with isolated neutral. They have selection or 40 or 100 amps, up to 100 amps, with where rated current is 5 amps. These 2 relays are for first instant stage. Next, what is K hash? What means hash? Is a designation for signaling relay. Do I have signaling relay? Oh, signaling relay. Oh. Old signaling relay shows nothing. Hey, you oh, yeah. Now, see, it shows inverted radiation. These are signal relays. Such relays, see, you don't know, line disconnected, what happens? Why? This box is equipped with 1, 2, 3 signal relays. One first shows instant zone, second is for delayed, and third overall. They will show this radiation mark if this branch was activated. They also have auxiliary contacts. Here, small auxiliary contacts used to indicate which panel is disconnected. Next object also not this one. special relay for output circuits. It's a delayed return relay. Has a coil as simple relays. And this copper cylinder. If you activate it, it strips, it closes these contacts. But when you remove voltage, current in this cylinder will keep it on for some, maybe for a second, maybe a bit longer. It's a special delayed deactivation relay. Why it's needed? Any idea? Why this relay lives here? Why fathers planted this special relay? Because for safety of operation, maybe I can tell for robustness. Time relay may see when have current, it may be some kind of not a stable contact, some kind of vibration. All the strips to guarantee what disconnection signal is held for time sufficient for switch to operate. This special delayed return relay is used. It's for safety. This is another version. Some set has this version. It small switch need 1-2 amps for operate. Large switch consume 5-6 amps in their disconnection coils. So here are quite massive contacts and massive. This copper cylinders ensures it will help us. I don't know, 1.5 seconds, something like this. This is disconnection pulse relay. Relay of delayed operation. This means delayed return. Pulse formation relay. To ensure what disconnection pulse is held well. And overall trip. This is trip signal. I draw instant branch. Now delayed branch. One. This part current bigger, this part current bigger. 1, 2, 3. Can you tell me why instant zone had 2 relays and delayed have 3? Why delayed operation zone was equipped with 3 relays, but instant only with 2? One, two, three for delayed zone, time delay, trip indicator, and output pulse circuit. Why we have 2 relays here and 3 here? Why fathers did it this way? When we spoke on incomplete start, our discussion in previous lecture, incomplete start, schematics for distribution transform. The distribution networks. Our previous lecture. There was a reason for relay in neutral wire. Why there was a necessity for relay in neutral wire? Why I needed neutral wire relays? is on the star side, BC fault in our case. For this transformer it will be BC. If fault is like this, what will we see on primary side? How many times should I repeat it? A, C, B, 100%, 50%, 50%. Two small currents and one big. This part operates only when fault is on line. It protects only beginning of line. Sometimes 10% is good. This part protects not only lines, it can be extended up to, it lasts for for bigger. Line, our text. We can, first zone will operate here. Second one can be extended below transformer. That's why it's mandatory, needs B-phase relay to get this current. To be sensitive for fault, not only line faults, but also here. These transformers, not all but most, belongs to our company. We protect them. So to make protection sensitive for faults at 0.4 kilovolt side, problem is what we have transformers delta star. For delta star transformer, B phase, control of phase B is mandatory. Without them, we can omit in isolated mode huge exclamation mark. If our network is isolated network, isolated neutral network. But here, in theory, we can omit B-phase current. If there would be no delta star transformers. To ensure what we control all area, including transformers. Regulation asks start from most powerful. If we have relatively uniform distribution of this taps, we can protect them all. If it's a situation 200, 250, 52 megawatts, we will be able to protect only 2 megawatts. Okay, this is designed from the 60s. Modern protection, will I have the Siemens operation sometimes? Here's modern protection. 1, 2, 3, 4, 5, 6, 6. Modern relays offer us not 2 zones. This old set proposes 2 zones. Modern propose 5 or 6. How can we create protection schematics for something? One, 2, 3, let's say I have a customer here. I bit simplified. Actually, I need to draw lots all along the line. I'm simplifying. B1. C1, C2, B1, B2, B3. A1, A2, A3, A4. Then, if needed, I can also activate A5. Good modern relays offer not 2, but 5 or 6. It's one tricky moment. Usually, 2 of them are reversible. We will speak about it when we speak on 2 side powered lines. But remember, what in block of 5 or 6, 2 are special with higher numbers. Usually, zones with higher numbers are special. Simple zones, like they can operate in simple mode, but take read manual carefully. 2 ones are special. Yeah, hello. Zones will be special. Okay, nice picture, but how can I create it? You like this picture? How can I create? For example, let's start here. This one coordinates with this transformer. I started with something. Okay. Let's assume this belongs to customer. I have 2 stages here, or 2 zones. One instant, one delayed. For instant, what can it be with red arrow? Fault, and this is max external fault. So, I nostra C1 is factor of schematics. This is factor of schematics. It depends on kind you have your current transformer. Digital transformer 1, full star 1. start without B relay 1. Current difference square root of 3. Oh, assume 1. What's this? It's from Latvian drošums. Factor of safety. It depends, first moment what it depends is what kind of transformer, what's a precision of your transformer. If you have ordinary 10P, 10. P means protection. What means 10? 10% error. If you have ordinary transformers with ray precision class 10P, this means what they are with error of 10%. For this case, safety factor is 1.1. If your company rich enough and bought you 5P, 5% P for protection, do not use metering transformer. Use 105. So it's a safety factor for error of your transformers. Usually relays are more precise than current transformer. So this is safety. I assume ordinary transformer 1.1. Here. Ratio of your transformer, for example, 1000 to 5. All, be careful, old style relays were programmed, or how to say, settings was in secondary amps. This formula gives me secondary amps. There are modern relays with old style where you program in amps as ampere meter shows, or relays what are programmed in primary amps. This means that you write 1000, but transformers are programmed as separate settings. Read your manual carefully. What you need to input, secondary amps or primary. Modern day, it's a style. It's just question of style. Anyway, there will be a secondary current. But, one more. There are relays where you program secondary amps. That means what you place this, you account for your current transformer ratio when you calculate settings. Or relays where you program primary amps. So, you do not take into account this when you calculate settings, but you need to program it into your relay as a separate element in settings table, and relay will divide for you. E external max, no? Meaning I1 here. Time for first zone is always 0. 0 or not so 0? Is 0. There is one moment. In old books tells 0 instantly, operates instantly. In modern life, you cannot operate instantly, but you can set a trip time, for example, 10 milliseconds. Actually, you have with masochistic approach, you can have trip in 1 millisecond. It's not good. I'll tell you where the problem is. All lines do have overvoltage protection. Lighting protection. Starting from simplest thing like spark discharges and ending with good devices like non-linear resistance, surge arresters. When your line is subject to what? Atmospheric overvoltage or simple lighting. Surge arresters will operate and they will create short circuit for a small period of time. Normal surge arresters are able to disconnect current. If you set trip time shorter than and return time of your surge arresters, you will get false trip. For this case, to prevent false trip when surge arresters are operate, you need operation time longer than expected current flow time from surge arresters. Longer than surge arresters operation time. For what this mean? 50 very good digit is 100 milliseconds. Do not set operation time of first zone to bear 0. Left some small space. Okay, you in rush, write 50 milliseconds. But left some space for surge arresters. Okay? Understood? Overvoltage protection with surge arresters. Stop eating your nails. Where am I? Yeah. It's an easy. Now, harder part. More complex here. What's an operation factor for the second zone, for this one? Where should I start calculating this? From the load current. Trip time, Latvian Nostra, of C2 will be factor of schematics, factor of safety, scheme means schematics, there means drošums, safety. Pārlaišana or startup or inrush. This is inrush factor. See what the moment is. When you connect your line to voltage, remember my first demonstration with current balance. What we saw? Startup current and false operation on startup current. To prevent false operation, trip setting should be increased. If my protection is a load, we are unlucky and we have load with inrush, any modern load has inrush. Something like this. Peak current of inrush and returns to goes back to normal load current. my delta T. Here is current I should deal with. Understand? Not the top instant, but load current at the point where it's counted. This full may be up to 5, 6, 7 times high. Here I will be in better position, approximately 1.2. It's highly, if you read old books, you will see that it's 1.1 for rural areas and 1.2 for modern, for industrial. It was a long time ago. 1.2 except serious when you will have special customer. What kind of special customer? Water treatment plants, water supply, oil pumping, gas pumping, loads with high power of large motors. Or area, these are prime customers. If you mess with water treatment plant, get ready for problems. If you mess with oil refinery, get ready for big problems. They do have quite high ratios of inrush or startup current. Also, you will see very high ratios of inrush, high penetration of air conditioning. Yes. Rich areas in hot climate. God save you. I ignore this in places like Saudi Arabia. They do have air conditioning even in doghouses. They are rich and they do not understand if you disconnect them on startup. Road crossing and sword. No, they way to discipline somewhat. So, if you have loads with high penetration of things like air conditioners, they do, see, industrial equipment do not start instantly all process. Usually it's some control system, even human-like. They start 1, 2, first pump, second pump, something. They do not start everything at all. Air conditioners are driven by temperature relays. They are dumb. If you had disconnection and power, huge amount of air conditioning or chillers or freezers, they all have their thermal relays in go position. When you connect line, all this amount of freon or coolant compressors starts instantly, and you have quite high inrush. For these cases, this factor, if ordinary load, something about 1.2, you can have 3 or even 5. Be careful. Be careful in Saudi Arabia. And best thing, you know what's the best thing? If your relay is smart enough and can record an oscillogram, take a startup oscillogram and calculate this factor. Or spend some time you can calculate it, but you should know inertia. It's a bit tricky. Best way is to record. Also, what you can do, create one zone, not create 2 zones this close trip time, but one first with high, with longer should be the one with some 30%, and in my case, let's say 1.5 delta t, and one with 5, let's say with this factor of 3, and 1 delta t. So create a more sensitive backup zone. Also, our next subject, current dependent delay, works well. So be careful with this factor when you have deep penetration of something like air conditioning. Or, on the other hand, deep penetration of thermal pumps. Scheme torsion divided by transformer rate and one more factor. It's in Latvian aggression. Aggression means return. Factor of return. E O at max. In my case, it's maximum load current. So what's this? What's a return factor? For old relays, magnetical resistance of, electromechanical relays, magnetical resistance of closed circuit much smaller than magnetical resistance of open, because air gap is smaller. That means what current needed to hold relay in trip position is much smaller than the current needed to move relay from open position to closed. It appears like this. Current output. If increase, this is E trip. When decrease, E return. Aggression coefficients or factor of hysteresis. Well, what is hysteresis? So factor of hysteresis for ordinary relay may be 0.3, 0.4. Oh, this is not good for current relays. For this old black relay, border of tolerance for commission 0.83. If less than 0.83, relay do not pass the commission. If above 0.83, it will go. It's fit for use. Oh, old digit was 0.83. Now, modern days, default is 0.95, 0.96. This means 4% margin. Why not 1? Because ideal current is ideal sign. Real one has noise. Also, come to visit sometimes hydropower plant. See all this. How it all shakes and vibrates. Add a margin of operation. If you don't have this hysteresis loop, relay will trip, return, trip, return, trip, return. Why we need it? So hysteresis of 4-5% is a good measure against this trip, return, against shake trip. Yeah. This factor plays no role for instant zones, but for delayed zones it's important. I can draw again this example. What is this? Inrush current. If I set like this, 1.1 approximately, this is trip current and this is return current. I took some relay with high difference. This means it's small. Here approximately 0. As I drawn it's approximately 0.5. See what happens? Huh? Relay stavok. Ko teiksi? What can you tell? What I draw? What will happen? You switch line, yeah? Your relay trips, and load comes back, load current returns to it, decreases to normal inrush process, and will your relay return? No, because return current is below load normal. If I do this way, it's a way to disaster. I need return current being above I need to take into account this hysteresis ratio, or I fail. Return factor of your relay for non-instant zone and max load current. Here is formula for last zone, more sensitive. Now, section B. What will be trip current for B1? To know, I need number 2. It's a maximum external current for line B, let's say. So, B1 will be scheme, safety, transformers, E2, meaning E max external. Clear? Clear. E trip current for B2. what it will be? Yes, schematic, safety. This is not activated by load, so no startup. Transformer. Non-instant zones. Instant zones return when current is zero. So for instant zone, we don't need to care about this ratio trip current, return current. For non-instant zones, okay, we have modern relay, so this 0.86. 4% difference between trip and return current into account. And what should I write here? They should understand. I need, you see, I need this gap. In this direction, it's delta t. In time, here it should be 10% in current. Understand? What defines this point? Trip current of C1, and it's calculated from point 1. Yes? So, here I should write what? In theory, E Nostrad C1. In reality, I1, and very important, safety factor square. This point calculated as a safety factor multiplied by this current. This point should have 10% safety margin relative to this point. This means safety factor square and max external current for adjustment or for next line. For next line, max external current. One, we jump one gap forward. And last one, it's a B3. It's schema, safety, startup, transformers, return, E. What? Max. In our case, it will be EL2 plus EL3. Here, how it works. First instant zone from max external current of my line. Second, max external current from the next line. Third will be max external. How calculated is this one? Safety square multiplied by first current. Understand why? And last from the load. Now important moment. You wrote all this. You place it to your supervisor, to inspector. How can we say this is good or this is not good? Important thing is a factor of sensitivity. utigums or sensitivity in Latvian. It's a for example, if nostra divided by I min iekšē minimal internal current. Important maybe needed, maybe not needed. Depends how you write. In primary amps or in secondary. If secondary, you need to place transformer radiator here. Setting for your here next zone protecting end of line divided by current of minimal internal fault should be sensitive factor should be greater or equal to 1.2. Sometimes if supervisor is your friend, you can pass with 115, but it's not a good. It's not always achievable. In case not achievable, it is possible to pass project with this. It is possible to sell. In 99% of cases, if you see what this zone not working, you abandon it and use next one. But if next one do not working, you in problem. This with extension of the this is zone 4. You in problem. Extension of the next zone, if so A2 not working, you do not achieve sensitivity. A3 works, okay. But if only load zone, only last, depends how well guys in high voltage network supervise you. If they are tough, you will have sometimes you have short limits based on system stability. Sometimes are very narrow. In this case, this will not work. You in trouble. There are some solutions, but not 100% working. If you have no strong limits on system stability, one zone's extension is okay. Okay. We can take a break, yeah? We have 2 lectures today. Or 1. Do you see your